Hello everyone, this is Chris, and this is the final video on the extra credit opportunity for trigonometry. And this video is to focus on the people who are really daring and they want to get a building's location on campus they don't have on the course map. So let's find something on the course map. Uh, where the heck? Oh, it's over here. Okay. Let's find the building that's not there. What are those called again? The Child Development Center? I do not remember what the Child Development Center is. Laurel, that's right. Laurel on there? Nope, cool. All right, let's say you want to do Laurel. I have no idea what that building looks like. I've seen it once in my life, and that's it. I walk by it every day, but I don't know where it is on the map. I mean, like, damn, I'm kind of screwed. Like, I know it's over here somewhere, but I don't really know where it is. This is where triangulation gets amazing. I'm not going to actually do triangulation because it's very specific for each case that you're in. Instead, I'm going to explain the reasoning behind why triangulation works and how to use it. So, this is the idea of triangulation. It's a triangle. So let me just wow, this is a really crappy triangle. So this right here is a triangle. I'm going to close it. So this is a triangle. I have no idea what the side lengths are, and I have no idea what the angles are. I literally just BS'd it. But I do know this is a triangle. And the only way that 3 points on the same coordinate plane cannot form a triangle is if those 3 points are on the same line. Like, this is not a triangle. That's a line. And that has something to do with the interior angle sum of a triangle. The interior angle sum of a shape is the quantity n minus 2, that quantity times 180, or 180n minus 360, where n is the number of sides. So there's 3 sides in a triangle, and so n minus 2, so 3 minus 2 is 1. 1 times 180. So there's 180 degrees. If you added up all the angles in the triangles, they're 180 degrees. That's kind of why. But so that's a slick formula for determining angle sum. But why does this matter? Why do we need to determine angle sum? What is angle sum going to help out with that other formulas are not really going to help? Is this idea that I have some arbitrary point right there. I have an arbitrary point. Can I fill it in with a hatch? Well, let me. Please work. Do the thing. So I want this to be solid. Okay. That's my point. That's my arbitrary point. I have no idea where it is. But apparently, I know the location of this point, and this point. In other words, I know the location of all the vertices of the triangle that makes up, well, this triangle. And then I can calculate something pretty crazy. Here's how triangulation works graphically. I take a map and I measure the distance. So yeah, that's fine. So what I do is, um, make these, let's make these cyan. And let's make the triangle, I'm being picky, let's make the triangle blue. All right. Okay. So what I do is I draw a circle starting from each of the vertices, and the radius of the circle is the distance that I measured with a ruler, or I measured with the core's website, 3 nearest sites. This is what's really cool about it. 3 nearest sites, 0.58 kilometers, 34.47. There are your 3 points. There are your 3 vertices of the triangle. I want a point right, well, I think Laurel is right here. So right where my cursor is, well, actually, let me put an X. I think that Laurel is right here. So let's say that I choose this as my location. I know the campus well enough. Let's pretend that I know the campus well enough that I actually know where this building is relative to these other places. So what I'm going to do is I'm going to approximate its location by taking the distances here, as many as I want. The more of them, the more accurate. I take as many of these distances that I want, and I make each of these distances a radius of a circle. And you might say, well, where am I going to put these? And that's kind of where triangulation gets funky. As you see, I know that this point is somewhere over here, and I know where the vertices are, and I actually know the length. And as you see, the place where all these circles intersect is this point. And by the way, your point is always wherever the circles intersect. What if all the circles don't intersect? Well, that's a really sad day. You're not wrong. What if this one's an overestimate, right? Well, according to this, right? According to this point is inside of this region. But what you have to do is you have to look at your data and you have to say, okay, well, this is probably an overestimate and this is probably an underestimate. And if I decrease the overestimate and increase the underestimate, then I get a region that's probably more accurate, as you see here. And the more points that I have, as you see, I have 3 points here, and I screwed up 2 of them, and the whole thing is messed up. But if I had all 20 of these on here, then it would be very rare. It would be an algebra mistake to cause some sort of inaccuracy. And so what's happening with this is we need to be able to get the distance to this red X from any one of the points. But we also need a location for all of the points. And this is kind of where it gets a little bit screwy. We have an accepted origin point. The CMBB point is the accepted location point. And so what we're going to do is we write all of our anchor points in terms of our origin. In other words, screw this red X. I already put its coordinates down. Screw the red X. I'm going to go here. Well, let me make it a little bit more accurate. For argument's sake, let me make it more accurate. Oh, come on. Close enough. So, that's close enough. My rule of thumb is that if the tip of the balloon touches the center of the X, that's fine. That's accurate enough. So I have a spreadsheet here. Let me get it. Okay. So I have a spreadsheet that has data points. It has coordinates and coordinates and coordinates. And I did this last night because I wanted to explain what's happening here. I have what I call an origin point, but that's not the only point that is accurate. There are all 20 of these locations. The CMBB is obviously the one that it's closest to because it's on top. That's the one that's on top of it. But the P36 and the CMOD and the 245 and the 306 and the 310 and all of these are other points whose location is known incredibly precisely, just like the origin point. And so why this matters is because if I know where these are relative to where this is, then it narrows it down. Let's think about this graphically. Imagine that I have, well, whatever. I'll leave that stuff there. So imagine that I have this. So see this dotted line, this dashed line? Well, this dashed line kind of sucks. This dashed line is exactly what I want. I want a distance between this center and somewhere else. But I don't know what direction, and I don't know how far. And so really this entire thing spans the entire coordinate grid. This thing goes through the entire coordinate grid. It can go anywhere I want it to be. But as soon as I find these distances, then it only limits the radius. It still is an unlimited range. It's still an unlimited direction that I can go into. But now it's a limited distance. So here's what you have to have for triangulation. You need, this is a requirement, this is a mathematical requirement. To triangulate a point, you need at least 3 data locations, 3 anchor points. Each of these vertices are called anchor points. You need at least 3 of them. The more the merrier, but you need at least 3 of them. And for this project, a maximum of 19 anchor points, because the 20th one is, or the first one is really just the origin point, which doesn't count. So a maximum of 19 as far as this project is concerned, and a minimum of 3. And subsequently, you need 1 direction. You need 1 angle. Otherwise, you're going to be chasing this thing around the circle for hours, and it's never going to work because it's mathematically impossible. And that's what these lines are for. These lines represent the heading for the potential bearing of these vectors. And actually, these are correct. These are not potential anymore. But notice that each of these radii, so this right here, this red circle, is a circle that represents the distance between the origin point and the P306 anchor point. And that same circle is copied over here to prove that it actually goes through it. This is the anchor point. This is an anchor point. This is an anchor point. This is an anchor point. It doesn't matter how many anchor points you have. It also doesn't matter where they are. If you have two anchor points that are on the same line, who cares? Use one of them. Use two of them. Because even though they're on the same line, they might not form a triangle, but they definitely won't form a triangle, but they might not. Okay, so they might not form a triangle, but they still provide different distance information. And you might say, well, Chris, there's less accuracy. When I calculated the vectors, the vector magnitude, it gave me a really long decimal. Well, yeah, so this is really accurate. And the core's website is not. The core's website is only accurate to every 10 meters. Well, this is good because what it's going to do is it's going to force you to create a region. And this region is really what you want. So notice that there was a region, right? It's going to force you to create this little region, and actually it's going to be bigger than this. And that region is going to represent the possible location of the building. Because please note that I don't know where Laurel is precisely. So it's not okay for me to say that it's right there and use the exact latitude and longitude coordinate for it. That's not okay. Instead, I need to use it as an approximation. Um, you can't use it without that. Now you can stop there because all of those places need to create a region. If you and let me put it this way, if you did it right, then all of those reference points, all those anchor points will create a region. Inside that region is going to be the building. And if you don't want to go any further, then make the center of that region your base point. And your tilt point can be some other place in the region that you have defined. I really don't care. If you're going to do this, you'll need to draw me a diagram and send me a picture of it so I know what the heck you're doing. So I actually know where your base point is. You're going to give me the radius for each of the points that you're using, and this is so I can check your work, but this is also so I can. There's different pieces of information that I might want to use instead in AutoCAD, and so I might just want to derive that information myself. So that's the way you can do it. If you want to get a precise location, you need one bearing. You need a bearing. Sorry, you need a heading. You have a bearing. That's the red X, but you need a heading to orient everything properly, and you need that bearing and heading off of your origin point. So you still need to do the same vector calculation as the second video, but it's not as dependent upon the math. This is more dependent upon the theory. It's more loosey goosey, so to speak. So if you decide to do this, the more base points, the better. And actually, the idea is the best base points, the best anchor points are not necessarily those sites because of the accuracy. The accuracy is going to give you a range, and the range is good for estimation because you don't really know where the building is. But simultaneously, if you want to be accurate, the range is bad. You want to reduce the range as much as possible. So the idea is what the best possible thing you can use is other people's base points as locations, as anchor points. Not only are they closer to the campus, but they have a higher decimal place of accuracy because it's the full latitude and longitude to a millionth of a decimal place instead of to the millionth place instead of to the hundredth place of a kilometer, right? So it's the nearest hundredth of a meter. It's the nearest centimeter and not to the nearest 10 meters. So there's a huge difference between there. And your region is going to be, again, if you do it right, your region is going to be a lot smaller. But this also, the higher accuracy also requires other people to do their base points first. So if you think you can do this whole thing quickly, then um, wait for other people to do their base points and then do it, and then work off of their work. Also, make sure that the base points that you do use have been verified by me. If someone comes up with a base point and it's just a piece of crap location, then I'm going to ask them to change the location. And if that's and then you don't want to have to redo your portion just because I asked someone to redo a base point on like maple or fir or dogwood. You don't want me to mess up your idea. So that's also why I chose. That's also why I have the base point and tilt point for tamarack, just in case. You have at least 1 point to start with. And then off of that, you can use some of these other sites. It's also imperative that you use the red X to get all these other sites. Otherwise, it's just going to give you the cursor latitude and longitude, which is fine, but it's only going to give you 3 sites. And one of those sites is always going to be your origin, so it's only going to give you 2 sites. So I hope that this kind of explains the idea of triangulation and specifically how to use triangulation to find coordinates and to really to approximate them is the idea. So thank you for watching these 3 videos. I really appreciate it. Again, please try to give me an email saying that you're interested, and I will respond with the given information, and some of this will be put on Canvas